And we are a magnetic levitator project. Before we get started with our specific levitator, we'd like to briefly touch on the design goals and the control system of the magnetic levitator project for anyone that is not familiar with the magnetic levitator. So our goal is to design and build a magnetic levitator that will suspend a metallic object underneath a solenoid for approximately 10 seconds. To achieve this, we need to balance the gravitational force against the electromagnetic force so that the object remains in a fixed position of our choosing. And to do this, it requires a feedback control system. The project is largely design-based, and there's not one set path to achieving our goal. And this allows us to bridge the gap between what we've learned in the classroom setting regarding feedback control theory and actual practice and implementation of a feedback control system to achieve a desired goal, and in this case, levitate an object underneath a solenoid. So to begin our levitator in particular, we would like to first discuss the structure we are using. As you can see from the picture on the left, we are using an entirely wooden structure, and we chose this for two main reasons. The first and arguably the foremost reason is that wood is cheap and easy to work with. This allowed us to build the structure to the exact specifications that we wanted, but in addition, we chose wood to avoid any potential magnetic interference that a metallic structure could pose to our levitator project. The next component that we are using is the solenoid, and the solenoid creates a magnetic field that can be changed and varied to our desired liking based on the amount of current that we provide from it from the controller. And we are opting for a machine wound solenoid as opposed to a hand wound solenoid, as machine wound solenoids tend to be tighter wound and more uniformly wound, which in turn allows the magnetic field to be more uniform and easier to work with when using a levitator. Our solenoid has approximately 350 turns in it, which might seem a little low compared to other solenoids, but we tested the solenoid out with various objects at varying distances and found that our solenoid is able to exert a significant magnetic field, and it'll be more than adequate for our project. In addition, the solenoid that we're using is small, and this allows the solenoid to be directly mounted onto our structure, and this was very nice to be able to directly mount it instead of having to worry about affixing it to the actual structure. So the next component that we are using is the sensor, and the sensor is arguably the most important component of our project because the sensor can detect the distance, and in turn that's the variable that the controller will be using to adjust the magnetic field of the object. And so we went through quite a few sensors before settling on the one we were using. We went through a Hall sensor and an infrared sensor before deciding that we were going to be moving forward with the ultrasonic sensor. And the way an ultrasonic sensor works is very similar to echolocation in that it emits a sound pulse and times how long it takes for the sound pulse to bounce off of an object and come back to it. And from that time, using the equation shown below, we are able to convert it to a distance in centimeters, which our controller will use to control the position and current provided to the solenoid. And the sensor that we're using in particular allows for a stable signal to be produced within 5 meters, which is more than adequate for our design, as we're only dealing with a possible range of 20 centimeters between the solenoid and the sensor. And the sensor provides a frequency of 40 hertz, which we deemed as an acceptable rate of times per second that the distance is being provided to our controller. From the controller, the way we are able to control the actual current provided at the solenoid is using a transistor. We are using a 5 amp transistor because we are only dealing with currents that are varying between 0 and 3 amps, so a 5 amp transistor is more than adequate to adjust the current provided to the solenoid. The object we are using is a magnet shown below, and we found that the magnet is able to be picked up by our solenoid at approximately 10 centimeters below the solenoid, which allows it to have a very good range of possible set point positions that we are using. And so now that we've talked about the physical aspects of our levitator, we'd like to briefly touch on the theory design that we are using. After implementing loop reduction and modeling, we are able to obtain the transfer function shown here. And to build that transfer function, we used a PD controller, and alpha and beta are process constants that we determined through mathematical descriptions of the process. And to realize this theoretical control, we are using a digital solution, in particular the Arduino Uno. And we are also going to use the inbuilt PID library system that comes with Arduino to allow for the controller to have a quick response to changes in the distance. So here's the actual code that we're using in Arduino, and we're not going to walk through every line by line, but we're including this to describe our process within the controller. So here we set all of our variables, set all of the pins that we are using in Arduino, assigning what pin corresponds to what variable. Here is our set point, which we measured to be 10.5 centimeters. We initialize the PID controller. We get in the distance from the sensor. We initialize our variables of KP and KD, aka set them, and we will discuss that in a second, how we set KP and KD. And then we send the values of KP and KD to our controller, which in turn computes the response in terms of current needed to be sent to the solenoid, which is sent to our transistor pins shown here. So, as I mentioned in the last slide, we are able to adjust our values of KP and KD, and we are using potentiometers to do this. Shown below is the potentiometer that we're using to change KP, and here's the potentiometer used to change KD. This allows KP and KD to be adjusted on the fly, and that allows us to fine-tune the values of KP and KD that we would like to have to achieve the most stable system. And this is an advantageous approach to setting KP and KD variables within our controller, because this prevents us having to manually enter in different values of KP and KD in Arduino code and uploading it to Arduino every single time we would like to adjust the values of KP and KD within our system. Here's a completed picture of our solution. As you can see, our sensor is mounted directly underneath the solenoid, and this is where the object will levitate. This picture is a picture of our circuit, and you can see that our controller, the Arduino Uno, is connected to the sensor, which gives a distance to the controller. And here is the potentiometer for KD, and this is a potentiometer for KD. And we can set those, and the output from the Arduino is sent to the transistor, which is connected to the power supply, which is then sent to the solenoid. Here's a video demonstration of our project. As you can see from that video, our project is not functioning as we would like it to. And the reason why we believe that this is not working is that we were able to adjust the potentiometers and the values of KP and KD as planned, as shown by this code excerpt that was provided real time from our controller. In addition to being able to adjust the KP and KD values, the distance sensor was working fantastically in providing real-time distance updates. And so we, as you can see from the controller output, we found that the controller was always outputting a value of 0 regardless of the varying KP and KD variables and the distance. And we think that this is happening because the PID library is always returning a output value of 0, and this caused a solenoid to function as a magnet instead of a levitator, because the inbuilt function was always returning a value to the transistor that was telling it to give the full magnetic force regardless of the distance. And this actually melted our board because the transistor was operating at full current instead of regulating the current, because it was doing as it was told from the PID library, which was not adequately changing the value provided to the transistor. And we tried to diagnose this issue because this is actually a very interesting issue, because not only did it always output a value of 0, but the KP and KD variables became unresponsive after being fed to it. So we spent quite a few days trying to diagnose the problem within our code, and we consulted many online resources and tutorials and fact sheets about the internal PID library, but ultimately we're unable to diagnose what exactly was wrong with the PID library, and we tried many approaches such as manually feeding values to the PID library just to see what the output would be, and it always remained 0 from the internal PID library. So we were very frustrated by that, but overall, this project was great in that it allowed us to bridge the gap between a theory that we spent all semester learning in the classroom setting to an actual application of a magnetic levitator. And so we really enjoyed this project, and we would highly recommend it for anyone. So thank you for your time, and we look forward to hearing about your guys' projects.